In this video, I will discuss the results of the compression after impact experiments. Let's start with the impact results. This image shows a 3D view of a typical post-impact C-scan. The specimen was impacted from above, looking in this orientation. As would be expected, delaminations occurred at each interface aligned with the local fiber orientation. This image shows a top view of a typical post-impact C-scan for a reinforced specimen. Overlaying a to-scale drawing with the approximate locations of the tabs, we can see that the delaminations were large enough to interact with quite a few tabs. We analyzed all the C-scans to find the projected delamination area for each specimen. Combining all the data, we can see that for the reinforced specimens, the delamination area was reduced by 11.4%. The reinforcement units were therefore able to improve the damage resistance of the specimen. Now let's look at the results of the compression tests. The average compression after impact strength of the reinforced specimens was 5.1% higher than that of the baseline specimens. However, the variability of the compression after impact strength was also much higher for the reinforced specimens. The consequence of this is that the difference in compression strengths is not statistically significant. Given the improvement in delamination area and mode 1 fracture toughness, the lack of improvement of compression after impact strength is somewhat unexpected. However, this lack of improvement can be explained by the following hypothesis. This image shows the photograph of the back face of a specimen after it was impacted. We see clearly signs of fiber damage, and if we zoom in, we can even find evidence of damage to the 0-degree fibers. Due to the presence of this fiber damage, the critical damage mode triggering final failure of the composite will change. It is usually assumed that unstable delamination growth or local buckling are the critical damage mode. However, once fiber damage is present, it is the stress concentrations around these broken fibers that will trigger the final failure by initiating further fiber damage in the material. Nettles and Sharber have also recently published research showing that it is stress concentrations around damage which trigger final failure during compression after impact. Consequently, we expect that at lower impact energies, where there will be less fiber damage, our reinforcements will be more effective at improving the compression after impact strength. To conclude, in these videos we have presented our research into the creation of interlocked thin-ply reinforcements, which can be used to reinforce selected interfaces of a regular composite layup. These reinforcement units were able to improve mode 1 fracture toughness as well as post-impact delamination area. Traditionally, researchers have sought to improve compression after impact strength by improving the interlaminar fracture toughness, for example with interleaves or translaminar reinforcements. Our results suggest that to obtain further improvements to compression after impact strength, especially at higher impact energies, we should instead focus on preventing or ameliorating fiber damage. We believe that we have only started unlocking the potential of ply-level and interfacial structures and are continuing to develop exciting new concepts in this area. So, if you have any questions or comments regarding our work, please don't hesitate to get in touch via any of the avenues shown on the screen or via the contact details displayed on this website. Thank you for watching these videos, and goodbye.